The moment of impact is a process of near instantaneous and total energy conversion. All of that incredible kinetic energy is released in a fraction of a second, in an explosion that can be thousands or even millions of times more powerful than the entire world's nuclear arsenal combined. This energy vaporizes the asteroid itself and a huge chunk of the Earth's crust, creating a brilliant, expanding fireball. At the same time, it sends a colossal shockwave traveling outwards through the planet's rock. This shockwave is what creates the crater. The process is a bit like a slow-motion splash in a pond. The initial impact pushes rock downwards and outwards, creating a deep, bowl-shaped transient crater. Then, in the seconds that follow, the rock, behaving like a liquid under this immense pressure, rebounds. The floor of the crater heaves upwards, creating a central peak or a ring of mountains, before the whole thing settles down into its final complex crater shape. The entire violent process of creating a crater that might be 100 kilometers wide can be over in just a few minutes. The immediate effects in the surrounding area are, to put it mildly, apocalyptic. A massive fireball would radiate out from the impact site, incinerating everything for hundreds of kilometers. A powerful air blast, a shock wave traveling through the atmosphere, would flatten forests and buildings even farther away. And if the impact happens in an ocean, it would create a mega-tsunami, a wave of water hundreds or even thousands of meters high that would travel across the entire ocean basin, scouring coastlines a world away. And all of this is just the beginning. The truly planet-altering effects are the ones that come later. The long-term, global effects of a major impact are what can truly threaten life on a planetary scale. The most significant of these is the impact winter. The colossal explosion blasts a huge amount of pulverized rock, dust, and vaporized material high up into the stratosphere. At the same time, the immense heat can ignite continent-spanning wildfires, which would send a thick layer of soot into the upper atmosphere as well. This fine dust and soot would then spread around the entire globe, creating a thick, dark veil that would block out the light of the sun. The sky would go dark, and it would stay dark, not for a few days, but for months or even years. Without sunlight, the Earth's surface would rapidly cool down, plunging the planet into a sudden artificial winter. This is the real killer. The darkness and the cold would cause a complete collapse of the global food chain. On land, the plants would wither and die without sunlight. The herbivores that ate the plants would starve, and the carnivores that ate the herbivores would follow soon after. The same thing would happen in the oceans, where the phytoplankton at the base of the food chain would die off, leading to a collapse of marine ecosystems. In addition to the darkness and the cold, the impact would also cause severe chemical changes in the atmosphere. The intense heat of the re-entering debris could create huge amounts of nitrogen oxides, leading to a period of intense planet-wide acid rain. It is this combination of immediate, violent destruction, followed by a long, slow, and quiet period of darkness, cold, and poison, that makes a large impact event one of the most effective ways to cause a mass extinction. And our planet, we now know, has experienced this process many times in its long and violent history.
Now, this understanding of impacts as a major geological force is actually a very new idea. For most of scientific history, the idea that rocks could fall from the sky and shape our world was considered absurd. This brings us to the quiet, human story of how we came to accept this profound and unsettling truth. For a long time, the dominant theory in geology was uniformitarianism. This is the idea that the Earth was shaped by slow, gradual processes like erosion and volcanism, acting over immense periods of time. The idea of sudden global catastrophes was seen as unscientific, a throwback to old biblical ideas about floods and fire. Craters on the Earth were almost always assumed to be the remnants of old, extinct volcanoes. The Moon was obviously covered in craters, but that was seen as a different, dead world. Earth was thought to be a safe, self-contained system. The man who did more than anyone else to change this view was a brilliant and tenacious geologist named Eugene Shoemaker. In the 1950s and 60s, Shoemaker meticulously studied craters like the famous Meteor Crater in Arizona. He showed, by finding unique, shocked minerals that can only be formed under incredible pressure, that these were not volcanic features, but were definitively caused by impacts from space. He was the founder of the field of astrogeology, and he had a profound and beautiful insight. He realized that the craters on the Moon were not just a curious feature of another world, they were a history book. Because the Moon has no erosion, it has preserved a perfect record of the impacts that have occurred in our corner of the solar system for billions of years. And by studying the Moon's craters, he reasoned, we could understand the history of impacts on our own geologically active planet, whose own scars have been mostly erased by time. He famously said, "Every crater on the Moon is a bomb crater, a quiet reminder of the violent history of our neighborhood."
Eugene Shoemaker's work slowly began to convince the scientific community that impacts were a real and important geological process. But it was still seen as something that happened in the distant past. The idea that a giant impact could have caused a recent mass extinction, like the one that killed the dinosaurs, was still considered a fringe and highly speculative idea. That all changed in 1980, with a quiet, brilliant discovery by a team of scientists at the University of California, Berkeley. The team was led by the Nobel Prize-winning physicist Luis Alvarez and his son, the geologist Walter Alvarez. They were studying a thin, strange layer of clay in the geological record in Italy. This clay layer marked the boundary between the Cretaceous period, the age of dinosaurs, and the Tertiary period, the age of mammals. It's called the KT boundary. They were analyzing the chemical composition of this thin clay layer, and they found something completely baffling. It contained an incredibly high concentration of the element iridium. Iridium is a metal that is very rare on the surface of the Earth, as most of it sank down to the core when the planet was molten. But it is relatively common in asteroids and comets. The Alvarez team realized that a thin, global layer of iridium-rich clay was the perfect fingerprint, the smoking gun of a massive asteroid impact. They calculated that a 10-kilometer-wide asteroid would have contained enough iridium to spread a thin layer all over the entire planet after it was vaporized in the impact. They published their theory that a single, catastrophic impact event had caused the mass extinction of the dinosaurs. The theory was met with fierce resistance from many paleontologists who still believed the dinosaurs had died out slowly from climate change or volcanism. The Alvarez theory was too dramatic, too catastrophic. But the evidence was powerful. In the years that followed, this same iridium anomaly was found at the KT boundary in dozens of other locations all around the world. The evidence was global. The only thing missing was the crater. The search was on for the murder weapon.
For the next 10 years, geologists searched for a massive impact crater, about 150 to 200 kilometers in diameter, that was exactly 66 million years old, but they couldn't find one. The problem is that the Earth is very good at hiding its scars. Plate tectonics, erosion, and sedimentation have erased most of the ancient craters on its surface. But the clues started to come together. Geologists found strange, thick deposits of tsunami debris from the same time period all around the Gulf of Mexico. This suggested the impact had happened somewhere in that region. Then, a geophysicist named Glenn Penfield, who had been working for an oil company in the 1970s, remembered some strange circular gravitational and magnetic anomalies he had seen in the data off the coast of Mexico's Yucatán Peninsula. At the time, his company wouldn't let him publish his findings, but he suspected he had found a giant buried impact crater. Finally, in the early 1990s, all the pieces came together. Researchers went back and reanalyzed the old data and drilled new core samples, and they confirmed it. Buried beneath a kilometer of younger limestone, centered on the modern-day town of Chicxulub, was a colossal impact crater, about 180 kilometers in diameter, and it was dated to exactly 66 million years ago. They had found it, the quiet, hidden scar of the dinosaur killer. This discovery was the final, beautiful confirmation of the Alvarez hypothesis. It was a stunning victory for this new, catastrophic view of Earth's history. It proved that our planet's evolution is not just a slow, gradual process, but is punctuated by sudden, violent events from the cosmos. And with that quiet, historical context in mind, let's now travel back in time to that fateful day.
All right. We have explored the brutal, quiet physics of a cosmic impact and the slow, patient detective work that brought this forgotten force of nature back into our scientific understanding. Now, let's use that understanding to travel back in time. We are heading back 66 million years to the very end of the late Cretaceous period, and we are going to visit the scene of the most famous and most consequential impact event in the known history of our planet. This is the story of the Chicxulub Impactor, the dinosaur killer. To truly appreciate the sheer, world-shattering scale of this event, we first have to paint a picture of the world it was about to change forever. The Earth, 66 million years ago, was a profoundly different and deeply alien place. It was a greenhouse world. There were no permanent polar ice caps, and the global average temperature was much higher than it is today. The sea levels were so high that a vast, shallow ocean, the Western Interior Seaway, ran right through the middle of North America, effectively splitting it into two separate continents. The plant life was also different. While flowering plants, which had evolved relatively recently, were becoming common, the landscape was still dominated by ancient-looking flora, vast forests of conifers, cycads, and giant ferns. It was a humid, lush, and almost tropical world, from the equator nearly all the way to the poles. And this warm, lush world was, of course, ruled by the dinosaurs. For over 150 million years, they had been the undisputed masters of this planet. The diversity and scale of these creatures is almost beyond our imagination. Herds of giant horned triceratops, each one as heavy as an elephant, would have moved through the ancient forests. Duck-billed hadrosaurs, some of which could walk on two legs, would have browsed on the vegetation. And above them all, in the warm, thick air, soared the pterosaurs, the giant flying reptiles, some with wingspans as wide as a modern fighter jet. The oceans were filled with their own monsters, the giant long-necked plesiosaurs and the ferocious apex predator mosasaurs. It was a stable, vibrant, and incredibly ancient ecosystem, the absolute peak of the age of reptiles.
Into this ancient, stable world of giants, a visitor was arriving. It had likely been traveling on its current path for millions of years, its long, quiet orbit around the sun finally bringing it into a collision course with Earth. It was an asteroid, or perhaps the core of a comet, made of dense rock and metal. And it was colossal. Scientists estimate it was somewhere between 10 and 15 kilometers in diameter. That is the size of Mount Everest, a literal mountain, falling out of the sky. And it was moving at a speed that is almost impossible to comprehend.
Its velocity is estimated to have been about 20 kilometers per second. That's about 72,000 kilometers per hour, or 45,000 miles per hour. It was moving so fast that it could have crossed the entire Atlantic Ocean in about 5 minutes. For the final few moments of its long journey, it would have become a spectacular and terrifying sight in the Cretaceous sky. As it hit the upper atmosphere, the compression of the air in front of it would have created a fireball of unimaginable brilliance, a light far, far brighter than the sun itself. Any creature on that side of the planet that happened to look up would have seen a new, terrible star in their sky, a star that grew in size and intensity with terrifying speed. The air itself would have been superheated into a plasma, and a colossal shock wave would have begun to form. The object was on a trajectory that would take it into the shallow tropical sea that we now know as the Gulf of Mexico. Its angle of approach was a steep one, perhaps about 60 degrees, and this steep angle would prove to be particularly deadly. It meant that the impact would blast debris and vaporized rock not just upwards, but preferentially northwards, directly towards the continent of North America. The final, quiet moments of the age of dinosaurs were ticking away.
The moment of the Chicxulub Impact is a moment that is almost beyond the power of words to describe. It is a moment of pure planetary scale physics. The instant the 10-kilometer-wide asteroid struck the shallow sea and the limestone-rich crust of the Yucatán Peninsula, its almost unimaginable kinetic energy was converted into a colossal explosion. The estimated energy release was equivalent to about 100 trillion tons of TNT. For comparison, the most powerful nuclear bomb ever detonated, the Tsar Bomba, was about 50 million tons of TNT. This impact was 2 million times more powerful than that. It was an explosion that literally shook the entire planet to its core. In the first fraction of a second, the asteroid itself and a huge chunk of the Earth's crust beneath it, thousands of cubic kilometers of rock, were completely vaporized, creating a transient cavity in the ground over 30 kilometers deep and 100 kilometers wide. The pressure and temperature at ground zero were far hotter than the surface of the sun, briefly creating a new, hellish star on the surface of the Earth. This initial impact blasted a colossal hole in our planet's atmosphere, sending a plume of vaporized rock, dust, and superheated gas ejecting all the way back out into space. At the same time, the impact sent a titanic seismic shockwave, a planet-spanning earthquake, traveling outwards through the planet's crust. It is estimated that this earthquake would have had a magnitude of 11 or 12 on the Richter scale, far more powerful than any earthquake ever recorded in human history. The ground would have been shaking violently all over the entire planet. But for the inhabitants of this world, the earthquake was the least of their worries. The other immediate effects were far, far worse.
Because the impact occurred in a shallow sea, it immediately created a mega-tsunami of almost unimaginable proportions. The sudden displacement of trillions of tons of water and rock created a colossal initial splash. But the more profound effect came from the rebound of the crater floor. As the initial cavity collapsed, the rock in the center of the crater heaved upwards, forming a temporary central peak taller than the Himalayas before it too collapsed outwards. This process acted like a giant piston, creating a ring of waves that were, at their origin, estimated to be over a kilometer or nearly a mile high. This colossal wall of water would have raced outwards in all directions across the Gulf of Mexico. It would have completely scoured the island of Cuba and the coast of Florida, washing hundreds of miles inland. It would have then continued, wrapping around the planet. We have found the geological evidence for this giant tsunami in ancient sediments as far away as Texas, the Caribbean, and even on the other side of the Atlantic. In Texas, geologists have found a thick, chaotic layer of rubble and sand containing a strange mix of deep-sea fossils and burned tree trunks. Clear evidence of a massive wave that scraped the ocean floor and then washed deep into the continent. But even a mile-high tsunami was not the most widespread or the most deadly of the immediate effects. The most terrifying event was the moment the sky itself caught on fire. The immense amount of molten rock and debris that was blasted out into space by the impact, trillions of tons of it, did not just disappear. Most of it was on a suborbital trajectory. It flew up above the atmosphere for a few minutes like a shower of giant shotgun pellets, and then it began to fall back down all over the world.
As these trillions upon trillions of tiny, sand grain-sized droplets of melted rock, called spherules, re-entered the atmosphere all across the globe, they would have heated up from friction and would have glowed like tiny, brilliant meteors. The entire sky, all across the planet, from pole to pole, would have been filled with these glowing, re-entering particles. The collective effect of this global meteor shower would have been to turn the sky into a giant, planetary-scale pizza oven. The sheer amount of infrared radiation, or heat, from all these glowing spherules would have been so intense that it would have heated the surface air to hundreds of degrees Celsius. Any plant or animal that was out in the open, not sheltered underground in a burrow or deep in a body of water, would have been roasted alive in a matter of minutes. This incredible pulse of heat from the sky would have then ignited massive spontaneous wildfires on a continental scale. Any forests that had survived the initial air blast would have now burst into flames. It is likely that for a period of weeks or even months after the impact, a significant portion of the Earth's land surface was on fire. We have found the evidence for this global firestorm in the geological record. The thin clay layer that marks the KT boundary is not just rich in iridium, it is also filled with a huge amount of soot, the carbon residue from burned trees. In some places, this soot layer is so thick that it suggests that almost the entire biomass of the planet's forests was burned to the ground. It was a true global firestorm, a quiet, terrible event that marked the beginning of the end for so many of the creatures that had survived the initial impact. And after the fire came the long, quiet, and even deadlier darkness.
The combination of the fine, pulverized dust from the impact itself and the thick black soot from the global wildfires was blasted high up into the stratosphere. And there, above the weather, it would have stayed for a very long time. This thick, dark veil would have quickly enshrouded the entire planet, blocking out the light of the sun. The sky would have gone dark, and it would have stayed dark. Not completely pitch black, perhaps, but as dark as a deep, moonless twilight for months, and perhaps even for years. This was the impact winter. Without sunlight reaching the surface, the Earth's temperature would have plunged dramatically. The warm, greenhouse world of the Cretaceous would have been plunged into a sudden, artificial, and brutal winter. Photosynthesis on land and in the oceans would have shut down almost completely. The plants that had survived the firestorm now withered and died in the darkness and the cold. The phytoplankton in the oceans, which form the very base of the marine food chain, died off in massive numbers. And with the base of the food chain completely gone, the rest of the ecosystem began its slow, quiet, and inevitable collapse. The giant herbivorous dinosaurs like Triceratops and Edmontosaurus would have been the first to go, as their food sources vanished. And then the giant carnivorous dinosaurs like Tyrannosaurus rex, who preyed on the herbivores, would have starved soon after. The same process happened in the oceans, with the giant marine reptiles dying off as their food sources disappeared. The dinosaurs, the pterosaurs, the mosasaurs, the rulers of the Earth for 150 million years had survived the initial blast, the tsunami, and the firestorm.
but they could not survive the long, quiet, and patient darkness of the impact winter. It was a profound and dramatic reset of the planet's entire biosphere. It is estimated that about 75% of all species on the planet, both on land and in the sea, were wiped out in this single event.
Now, let's turn our attention to the quiet, brilliant detective story of how we pieced all of this together. The story of the Alvarez hypothesis. As we've said, the idea that an impact killed the dinosaurs was proposed in 1980 by a team that included the physicist Luis Alvarez and his geologist son, Walter Alvarez. Their investigation began with a simple, quiet question about a strange layer of rock. Walter Alvarez was studying a geological outcrop in Gubbio, Italy. He was looking at a thick layer of limestone rock that contained the fossilized remains of tiny marine creatures from the age of dinosaurs. And directly on top of that, there was another layer of limestone that contained the fossils of creatures from the age of mammals. And right between these two layers, there was a thin, half-inch thick layer of dark clay. This was the KT boundary, the line that marked the Great Mass Extinction. And his question was, how long did it take for that thin layer of clay to be deposited? Did the extinction happen slowly, over millions of years, or was it a sudden, catastrophic event? To try and answer this, he needed a way to measure the passage of time in the rock. He consulted with his father, Luis, a Nobel Prize-winning physicist. Luis suggested a clever, if slightly obscure, method. The Earth is constantly being showered with a fine dust of micrometeorites from space. This dust contains a small amount of the element iridium. So, by measuring the concentration of iridium in the clay layer, they could calculate how long it had taken to be deposited. They expected to find a very, very small amount. But when they got the results back from their analysis, the numbers were so high they thought their equipment was broken. The thin clay layer contained hundreds of times more iridium than any normal terrestrial rock. It was a colossal, global anomaly.
Where could all this extra iridium have possibly come from? The Alvarez team considered and ruled out a number of terrestrial explanations. It couldn't have been a supernova, as that would have also left behind a specific isotope of plutonium, which they did not find. The only explanation that seemed to fit all the facts was a truly extraordinary one. They proposed that the iridium anomaly was the fallout, the shrapnel, from a massive 100-kilometer-wide asteroid that had slammed into the Earth. They calculated that an asteroid of that size would contain enough iridium to spread a thin, detectable layer all over the entire planet after it was vaporized in the impact. And so, they published their radical theory in 1980. The Great Mass Extinction that killed the dinosaurs was caused by a single, catastrophic impact event. The reaction from the scientific community, particularly from the paleontologists, was, for the most part, fiercely negative. The paleontologists had long believed that the dinosaurs had died out slowly and gradually due to long-term climate change or increased volcanism. This new sudden and violent theory from a physicist and a geologist seemed to them to be an intrusion, a simplistic and overly dramatic explanation for a complex biological event. The debate raged for the next 10 years, but the evidence for the Alvarez hypothesis just kept getting stronger. Geologists all over the world began to look at the KT boundary layer in their own regions, and they found the iridium anomaly everywhere. They found it in deep sea cores from the bottom of the ocean. They found it in rock formations in Denmark, in Spain, in New Zealand. It was a truly global signal. They also found other telltale signs of a massive impact in this layer: shocked quartz, tiny glass spherules, and a thick layer of soot from the global wildfires. The evidence was overwhelming. The only thing missing was the crater, the giant 200-kilometer-wide smoking gun.
The quiet, decade-long hunt for the Chicxulub crater is one of the great detective stories in modern geology. Scientists knew what they were looking for: a massive impact crater,
about 180 to 200 kilometers in diameter, that was dated to exactly 66 million years ago. But finding such a crater on an active, geologically dynamic planet like Earth is incredibly difficult. Most craters on land are quickly erased by erosion from wind and water, and craters in the ocean are covered by kilometers of water and then slowly buried by sediment. But there were clues. All around the Gulf of Mexico, geologists had found strange, thick deposits of jumbled rock and tsunami debris that were dated to the end of the Cretaceous. This suggested that the impact had happened somewhere in that region, either in the Gulf itself or on the surrounding land. The key piece of the puzzle came from a geophysicist named Glenn Penfield. In the late 1970s, while working for a Mexican state-owned oil company, he had been analyzing magnetic and gravitational survey data for the Yucatán Peninsula. In his data, he saw the faint, ghostly signature of a huge, perfectly circular, buried arc stretching from the northern coast of the peninsula out into the Gulf of Mexico. It looked exactly like the signature of a giant impact crater. At the time, his company wouldn't let him publish his findings, as it was proprietary data related to oil exploration. But he knew he had found something special. In the early 1990s, after the Alvarez theory had become well known, Penfield and other researchers were able to connect the dots. They went back and reanalyzed the old geophysical data. They also looked at core samples that had been drilled in the area for oil exploration, and they found telltale signs of shocked quartz and melted rock, the definitive fingerprints of a massive impact.
It was all there, buried beneath a kilometer of younger limestone, centered on the modern-day town of Chicxulub Pueblo, was a colossal impact crater. It was about 180 kilometers in diameter. And when they dated the melted rock from the impact, it was exactly 66 million years old. They had found it. This was the quiet, hidden, and almost perfectly preserved scar of the dinosaur killer. The discovery of the Chicxulub crater was the final, triumphant confirmation of the Alvarez hypothesis. It was a stunning victory for this new, more catastrophic view of Earth's history. It proved beyond any reasonable doubt that our planet's evolution is not just a slow, gradual, and peaceful process. It is a story that is punctuated by sudden, violent, and transformative events from the cosmos. The quiet, faded ring buried beneath the Yucatán Peninsula is a permanent reminder of that profound truth. And now, for the final chapter of this part of our story, let's look at the quiet, biological aftermath. The rise of the mammals. The Chicxulub impact was an event of almost unimaginable destruction. It was one of the worst days in the history of life on Earth. But for every great extinction, there was a new beginning. For the entire 150 million year reign of the dinosaurs, our own distant ancestors, the mammals, were small, marginal creatures. Most of them were no bigger than a rat or a shrew. They were mostly nocturnal, living in burrows or in the trees, just trying to survive in a world dominated by giants. But they were adaptable. And when the Great Impact happened and the world was plunged into darkness and cold, their small size and their warm-blooded metabolism may have been the very things that allowed them to survive. While the giant, cold-blooded dinosaurs, with their huge appetites, starved, our small, furry ancestors were able to survive on a diet of insects, seeds, and roots, huddling in their burrows to wait out the long winter. When the dust finally settled and the sun returned, they emerged into a new, empty world. The great dinosaurs were gone. The immense ecological niches that they had occupied for millions of years were now vacant. And into that empty space, the mammals exploded. It was a period of incredible, rapid evolution and diversification. In the quiet, post-apocalyptic world that followed the Great Impact, the age of mammals began. And that long, winding, 66 million year long evolutionary road would eventually lead to the primates, and then to the hominids, and then, finally, to us.
The story of the Chicxulub Impact is a quiet, powerful reminder of our own good fortune, a cosmic accident that cleared the way for our own existence. Now, let's leave the relatively recent past of 66 million years ago and travel much deeper into our planet's history to explore the even larger, more ancient, and more obscure impact scars that are hidden in the deep time of the geological record. We begin our tour of these ancient ghosts in South Africa. Here, you will find a structure known as the Vredefort Dome. It is not a dramatic, bowl-shaped crater like the ones on the Moon. It is a vast, heavily eroded ring of hills over 70 kilometers in diameter. For a long time, geologists debated its origin, with many believing it to be a strange, ancient volcanic feature. But the quiet, overwhelming evidence, particularly the presence of telltale shocked minerals, has confirmed its true identity. The Vredefort Dome is the central, uplifted root of the largest and oldest confirmed impact structure ever found on planet Earth. The impact that created this structure occurred an almost unimaginable 2 billion years ago. The world at that time would have been completely alien to us. The continents were in a different configuration, the atmosphere had very little oxygen, and life on Earth consisted only of simple, single-celled organisms like bacteria and algae quietly living in the oceans. It was into this ancient microbial world that a truly colossal object arrived. The asteroid that created the Vredefort structure is estimated to have been even larger than the one that killed the dinosaurs, perhaps as wide as 15 to 20 kilometers. When it slammed into the Earth, it created a transient crater that is thought to have been up to 300 kilometers, or nearly 200 miles in diameter. It is, by a significant margin, the largest impact scar we have ever found on our planet.
The Vredefort Impact Event is a quiet study in the almost unimaginable power of cosmic collisions. The energy released by this single impact would have been many times greater than the Chicxulub event. The immediate, local effects would have been apocalyptic, vaporizing a huge section of the Earth's crust and creating a temporary hole in the atmosphere. The global effects would have been even more profound. The impact would have sent a colossal cloud of pulverized rock and water vapor into the atmosphere, likely enshrouding the entire planet in a thick, dark haze that could have lasted for years, or even decades. This would have caused a dramatic and long-lasting impact winter, plunging the globe into a deep freeze. This event would have had a massive, sterilizing effect on the simple life that existed at the time. But even more profoundly, it may have permanently altered the course of our planet's evolution. Some scientists have speculated that an impact of this magnitude could have been powerful enough to trigger a new phase of plate tectonic activity, or to significantly alter the chemistry of the early atmosphere, perhaps even contributing to the eventual rise of oxygen. The quiet, humbling truth is that the history of our own planet is a story that has been profoundly shaped by these random, violent intrusions from the cosmos. The Vredefort Impact is a quiet, powerful reminder that the Earth is not an isolated system, but an active participant in the sometimes violent life of the solar system. The evidence of this colossal event is now faint, a ghost of a crater that has been worn down by 2 billion years of slow, patient erosion. But its scar, for those who know how to read the rocks, is still there, a quiet testament to one of the most violent days in our planet's long history.
So if the original Vredefort crater was up to 300 kilometers wide, why is the structure we see today, the dome, only about 70 kilometers across? This is a quiet lesson in how the Earth heals its deepest wounds. The structure we see today is not the crater itself, but the deep, underlying root of the impact. When the massive asteroid hit, it created that huge transient crater. But in the minutes that followed, the Earth's crust, behaving like a liquid under this immense pressure, rebounded. The very center of the crater floor was pushed upwards, creating a massive central peak. Over the 2 billion years that have passed since the impact, the upper layers of the crater, the rim, the ejecta blanket, the melted rock sheet, have been completely and totally erased by the slow, patient work of erosion from wind and water. What we are left with is the deep, underlying geological structure that was created by the impact. The Vredefort Dome is the remnant of that central uplift, the deep scar tissue of the planet's crust. Geologists can study the rocks in this dome, which were once buried many kilometers underground and were brought to the surface by the rebound, to learn about the deep structure of the Earth's crust. It's like a natural drill hole, a quiet window into the deep past. The story of how we came to understand this is another quiet detective story. For a long time, as we said, the Vredefort structure was thought to be volcanic. But in the 1960s, geologists began to find unique geological features in the area that could only be formed by the extreme shock pressures of a massive impact. They found shatter cones, which are distinct cone-shaped patterns in the rock that are a definitive fingerprint of a hypervelocity impact. They also found shocked quartz and other minerals that had been altered at a microscopic level by the intense pressure wave. It was this quiet, meticulous geological detective work that finally, in the 1990s, led to the universal scientific consensus that Vredefort was, indeed, the scar of the world's largest known impact.
Now let's travel from the plains of South Africa to the forests of Ontario, Canada, for our next great scar. Here we find the Sudbury Basin. This is another incredibly ancient and massive impact structure, second only to Vredefort in size. The impact that created it occurred about 1.8 billion years ago, and it tells its own unique and surprisingly lucrative story. The Sudbury impact was caused by a large comet or asteroid, estimated to be about 10 to 15 kilometers in diameter, the same size as the dinosaur killer. It created a crater that was originally about 250 kilometers across. And just like Vredefort, the original crater has been heavily eroded and deformed by geological processes over the last nearly 2 billion years. What we see today is the remnant of that structure, an oval-shaped basin that is now home to a thriving city and a major mining district. But the Sudbury impact has a unique and fascinating feature that sets it apart from all others. The impact is thought to have been so incredibly powerful that it didn't just create a crater in the Earth's crust, it ruptured the crust entirely. Imagine the impact like a colossal cannonball, punching a temporary hole right through the several dozen kilometer thick crust and exposing the superheated molten rock of the Earth's upper mantle below. This had a profound consequence. The planet's own molten mantle, rich in heavy metals like nickel, copper, and platinum, would have welled up from below to fill the bottom of the crater. This upwelling of mantle material then mixed with the rock that had been melted by the impact itself, creating a huge, thick sheet of molten rock and metal at the base of the crater. It was a temporary, man-made, or rather, asteroid-made, magma chamber.
And this brings us to the quiet, strange, and incredibly valuable legacy of this cosmic catastrophe. As this giant sheet of melted rock and mantle material slowly cooled over thousands of years, the heavier materials, the metals, began to separate out, a process called differentiation. The dense molten nickel, copper,
platinum, and other precious metals sank to the bottom of the melt sheet, where they became concentrated in a thick, incredibly rich layer of ore. And that is why the Sudbury Basin today is one of the single richest mining districts on the entire planet. It is the world's largest supplier of nickel and a major producer of copper and platinum group metals. The city of Sudbury exists and has thrived for over a century because of the immense mineral wealth that was created in the fiery aftermath of this ancient cosmic collision. It's a quiet and profound irony, a random act of celestial violence from 1.8 billion years ago is directly responsible for the modern economy of an entire region. The materials that we use for our stainless steel, our electronics, and our industrial processes were, in this case, a direct gift from a giant rock that fell out of the sky. The Sudbury Basin is a quiet, powerful reminder that these great impact events are not just stories of destruction, they're also stories of creation, of profound geological change that can have unexpected and long-lasting consequences. The evidence for the Sudbury impact is, just like at Vredefort, overwhelming. The region is filled with shatter cones, and the basin itself is underlain by this thick impact melt sheet. It is a quiet, beautiful, and undeniable scar on the ancient face of our planet.
Now let's take a quieter and more brief tour of a few of the other faded scars that are scattered across our planet's surface. While Chicxulub, Vredefort, and Sudbury are the big three, they are far from the only major impacts our planet has endured. Let's travel to the remote frozen landscape of Siberia. Here you will find the Papagaï crater. This crater is about 100 kilometers in diameter and was formed about 35 million years ago. It is a large and relatively recent impact, but what makes Papagaï so interesting is what was created in the impact. The asteroid slammed into a region that was very rich in graphite. The incredible pressure and heat of the impact instantly transformed this graphite into diamonds. It is estimated that the Papagaï crater contains a colossal deposit of impact diamonds, perhaps trillions of carats worth, more than all the other known diamond reserves on Earth combined. These are not gemstone-quality diamonds. They are small, industrial-grade diamonds. But they are a quiet, glittering testament to the incredible alchemical power of a cosmic collision. Now let's journey back to Canada, to Quebec. Here, you can see one of the most beautiful and visually striking of all impact craters from the air. This is the Manicouagan crater. The impact occurred about 214 million years ago, and it created a crater about 100 kilometers across. Over the eons, the crater has been heavily eroded by glaciers and other processes. What is left today is a beautiful ring-shaped lake about 70 kilometers in diameter that fills the eroded remnant of the crater. From the air, or from space, it looks like a perfect, shining blue ring, and it is often called the Eye of Quebec. The central peak of the crater forms a large island in the middle of the ring-shaped lake. It is a quiet, beautiful scar that has been transformed by time into a stunning natural landmark.
All right, We have spent a long time in the deep, ancient past exploring the ghostly, faded scars of colossal impacts from billions of years ago. For the final part of our journey tonight, let's travel forward in time to the modern era and look at the more recent and much smaller encounters our planet has had with visitors from space. And we will see how these events have shaped our new, quiet understanding and vigilance. We begin our modern tour in the year 1908 in a remote and sparsely populated region of Siberia. This is the story of the Tunguska event, one of the most powerful and mysterious impact events in recent history. On the morning of June 30th, local inhabitants and settlers in the region witnessed a remarkable and startling sight. An immense, brilliant meteor, described as being as bright as the sun, streaked across the morning sky. It was followed several minutes later by a series of deep, powerful booms and a tremor that shook the ground. The atmospheric shockwave from the event was immense. It radiated outwards, knocking down trees over a vast area of more than 2,000 square kilometers, an expanse larger than a major modern city. The effects were even seen far away. For several nights afterwards, the sky over Europe and Asia glowed with an unusual brightness, a result of dust scattered high into the atmosphere. It was a massive and powerful event. But here is the quiet, central mystery of Tunguska. When scientific expeditions finally made their way to the remote region years later, they found the forest, with the trees all knocked down in a radial pattern pointing away from a central point. But they did not find an impact crater. There was no hole in the ground.
Now let's journey back to North America, to Quebec, Canada. Here, if you look at a satellite image of the region, you can see one of the most beautiful and visually striking of all impact craters on Earth. This is the Manicouagan crater. The impact occurred about 214 million years ago, just before the age of the dinosaurs began. It created a crater that was originally about 100 kilometers across. Over the vast stretches of geological time since then, the crater has been heavily eroded, especially by the grinding action of the great ice sheets during the last ice age. What is left today is a beautiful, nearly perfect ring-shaped lake, about 70 kilometers in diameter, that fills the eroded remnant of the crater. From the air, or from the International Space Station, it looks like a perfect, shining blue ring in the middle of the Canadian wilderness. It is so striking that it is often called the Eye of Quebec. The central peak of the crater, which was created by the rebound of the rock after the impact, now forms a large, circular island, René Levasseur Island, in the middle of the ring-shaped lake. It is a quiet, beautiful scar that has been transformed by time and water into a stunning natural landmark. And it has a strange, quiet connection to other impacts. Some scientists have proposed that the Manicouagan impact may have been part of a multiple impact event, where a single large asteroid or comet broke up into several pieces before hitting the Earth, creating a chain of craters all across the planet. There are several other large craters of a similar age in places like France, Ukraine, and North Dakota. It's a tantalizing, though still debated, idea that our planet might have once been hit by a cosmic shotgun blast. All right, we have spent a long, quiet time in the deep, ancient past, exploring the ghostly, faded scars of colossal impacts from billions and millions of years ago. For the final part of our journey tonight, let's travel forward in time, to the modern era, to our own historical period, and look at the more recent and much smaller encounters our planet has had with visitors from space. And we will see how these events have shaped our new, quiet understanding and our modern-day vigilance. We begin our journey in the year 1908. We are in a remote, sparsely populated, and deeply forested region of Siberia in Russia. This is the story of the Tunguska event. It is one of the most powerful, most mysterious, and most well-documented impact events in all of recorded human history. On the morning of June 30, 1908, the local Tungus people, who were nomadic reindeer herders, and the few Russian settlers in the region, witnessed a spectacular and terrifying sight. A colossal fireball, which some described as being as bright as the sun, streaked across the morning sky. It was followed, a few minutes later, by a sound like a continuous barrage of artillery fire, and a shock wave so powerful that it felt like an earthquake, knocking people off their feet and shattering windows in towns hundreds of kilometers away. The shock wave from this event was so powerful, in fact, that it was detected by sensitive barometers and seismographs all across Europe. It traveled around the world twice. For several nights afterwards, the sky over Europe and Asia was so bright from dust that had been scattered high into the upper atmosphere that people reported being able to read a newspaper outside in the middle of the night. It was a massive, powerful event, an explosion that scientists now estimate was equivalent to about 15 megatons of TNT, about 1,000 times more powerful than the atomic bomb dropped on Hiroshima.
The first scientific expeditions to the remote Tunguska region were only able to make the difficult journey many years later. And what they found was a scene of incredible, quiet devastation. An area of over 2,000 square kilometers, an area larger than a major modern city like London or Tokyo, had been completely and totally flattened. An estimated 80 million trees had been knocked down, all of them lying in a radial pattern, like the spokes of a giant wheel, pointing away from a central point. But here is the quiet, central mystery of the Tunguska event, the thing that made it a puzzle for decades. At the center of this vast radial pattern of destruction, at the ground zero of the explosion, there was no impact crater. There was no hole in the ground. The trees at the very center were still standing, though they were stripped of all their branches, looking like a forest of giant telephone poles. This lack of a crater was a deep and enduring puzzle for a very long time. It led to all sorts of wild and speculative theories. Some proposed it was a natural gas explosion. Others suggested it was a collision with a tiny primordial black hole or an encounter with a piece of antimatter. Some even, of course, suggested it was the crash of an alien spaceship. But the quiet scientific consensus today is that the Tunguska event was the result of an airburst. The idea is that the object that caused the explosion was not a solid, strong metallic asteroid that could survive the journey to the ground. It was more likely a fragile, stony asteroid or a small comet. This object, estimated to be about 50 to 60 meters in diameter, entered the Earth's atmosphere at high speed. And as it plowed through the dense lower atmosphere, the immense pressure and the incredible heat caused it to completely disintegrate and explode while it was still several kilometers up in the air. So, the incredible destructive power of the event was unleashed not on the ground, but in the atmosphere. The shock wave from this mid-air explosion is what flattened the forest below. The object itself was completely vaporized, which is why there was no impact crater. The Tunguska event is a quiet, powerful, and slightly unsettling reminder that an object doesn't have to be a giant, dinosaur-killing mountain of rock to be incredibly dangerous. Even a relatively small, city block-sized asteroid or comet, if it explodes in our atmosphere at just the right altitude, can unleash the power of a large hydrogen bomb. It's a quiet reminder that these events are not just a feature of the ancient, deep past, but are a real and ongoing part of living in our dynamic solar system. The quiet sky is not always as peaceful as it looks. The eyewitness accounts from the event, collected from the local Tungus people years later, are a testament to the strangeness of the phenomenon. They described seeing the sky split in two, a great fire appearing that was so hot it felt like their shirts were on fire, even though they were dozens of kilometers away. This was followed by the immense shockwave and a sound like a sky full of falling rocks. For a long time, they considered the area to be cursed, a place to be avoided. The scientific expeditions that followed were a quiet saga in themselves.
The first, led by Leonid Kulik, only reached the remote site in the 1920s. They had to travel for weeks by train, by boat, and then by foot through the dense, swampy forest, or taiga. What they found was a scene of almost perfect geometric devastation. The radial pattern of the fallen trees all pointed back to a central point, allowing them to pinpoint the ground zero of the explosion. But the lack of a crater remained the central, baffling mystery. It's a beautiful example of how a real-world event can be so strange that it seems to defy easy explanation, leaving a quiet, enduring puzzle that would take the better part of a century to solve. Now let's jump forward over a century to a much more recent and much more well-documented modern encounter. This brings us to the Chelyabinsk meteor. Our story now takes us to the morning of February 15th, 2013, in the skies over the Russian city of Chelyabinsk, a bustling industrial city near the Ural Mountains. On this cold, clear winter morning, residents of the city, who were on their way to work or school, were treated to an incredible and, for many, terrifying sight. A superbolide, which is the term for an exceptionally bright meteor, streaked across the morning sky. It was not a gentle shooting star, it was a colossal, brilliant fireball, at its peak shining far brighter than the sun itself. People standing outside could feel an intense pulse of heat on their faces, and many reported seeing strange, unnerving shadows being cast by the object. The object that created this spectacle was an asteroid estimated to be about 20 meters, or about 65 feet, in diameter. It entered the Earth's atmosphere at a very shallow angle and at an incredible speed of over 19 kilometers per second. And just like the Tunguska object a century before it, it did not survive its fiery passage through the atmosphere. At an altitude of about 30 kilometers, the immense pressure of its hypersonic flight caused the asteroid to catastrophically explode in a massive airburst. This explosion was the most powerful such event ever recorded by the global network of infrasound sensors that are designed to detect nuclear tests. It released an amount of energy equivalent to about 500 kilotons of TNT, about 30 times more powerful than the atomic bomb that was dropped on Hiroshima. The brilliant flash of light from this explosion was visible for hundreds of kilometers around. But the most significant and most dangerous effect came a few minutes later, as the shock wave from the mid-air explosion, traveling at the much slower speed of sound, finally reached the city below.
The shock wave from the Chelyabinsk airburst hit the city with incredible, invisible force. The powerful acoustic wave shattered windows in over 7,000 buildings across the entire region. The sound of the explosion was a deafening boom that set off car alarms and rattled buildings to their foundations. Over 1,500 people were injured, and it's a quiet, interesting detail that none of these injuries were caused by the meteor itself. They were almost all caused by flying shards of broken glass from all the shattered windows. Many people, having seen the incredibly bright flash in the sky, had rushed to their windows to see what was happening and were standing right next to them when the shockwave hit a couple of minutes later. The Chelyabinsk meteor event was a profound moment for planetary science and for public awareness of this particular natural hazard. Unlike the Tunguska event, which happened in a remote, unobserved region a century ago, the Chelyabinsk event happened over a populated, modern city in the age of the internet and the dashboard camera. The fireball and its aftermath were captured on thousands of dash cams, security cameras, and cell phone videos. This incredible, crowdsourced collection of footage gave scientists an unprecedented amount of data to study. By analyzing the different videos from different locations, they were able to triangulate the asteroid's exact trajectory through the atmosphere with incredible accuracy. They could calculate its original orbit around the sun, its speed, its size, and the energy of its explosion. It was, in a very real sense, a quiet, cosmic wake-up call. It was a visceral and well-documented reminder that our solar system is still a cosmic shooting gallery,
and that these impact events, while rare, are a real and ongoing natural hazard. It was a powerful demonstration that even a relatively small 20-meter asteroid, an object that is incredibly difficult to detect in advance, can cause significant damage and injury if it happens to explode over a populated area.
The story of Chelyabinsk has a final, quiet, and very useful chapter. Because the asteroid exploded at a high altitude, most of it was vaporized. But many smaller fragments survived the explosion and continued to fall to the ground. In the days and weeks that followed, scientists and local residents began to search the snowy landscape for these fragments, these meteorites. The largest single piece, weighing over 500 kilograms, was recovered from the bottom of a frozen lake where it had punched a perfect, neat hole in the ice. These recovered meteorites were a scientific gold mine. They allowed scientists to directly study the composition of the object. They confirmed that it was a common type of stony chondrite asteroid, a pristine piece of leftover material from the formation of the solar system. By studying its chemistry, we can learn more about the raw materials that built our own planet. The Chelyabinsk event, as startling as it was, ultimately provided a huge impetus for a quiet but incredibly important field of astronomy. This brings us to our final chapter tonight, the story of our own quiet, watchful eyes on the sky, the science of planetary defense. This is the story of how we, for the first time in the 4.5 billion-year history of our planet, are beginning to develop the ability to see these threats coming and, perhaps, one day, to do something about them. We are no longer just passive victims waiting for the next big rock to fall. We are becoming active and hopefully wise guardians of our own small blue world. It is a quiet and deeply hopeful new chapter in our long relationship with the cosmos.
The modern effort to protect our planet from cosmic impacts begins with a simple but immense task: finding the asteroids. For the last few decades, a number of dedicated astronomical surveys, funded by NASA and other organizations, have been quietly scanning the skies every single clear night. Their job is to find, to track, and to categorize the near-Earth objects, or NEOs, the asteroids and comets whose orbits bring them into our planetary neighborhood. These are programs with wonderfully evocative names, like PanSTARRS, the Panoramic Survey Telescope and Rapid Response System in Hawaii, and the Catalina Sky Survey in Arizona. These are not the giant famous telescopes that take beautiful pictures of distant galaxies. They are specialized wide-field telescopes, designed to survey huge patches of the sky over and over again, looking for tiny, faint points of light that are moving against the background of the fixed stars. The process is a quiet and highly automated one. A telescope will take a series of pictures of the same patch of sky over the course of an hour. A computer then analyzes these images, looking for anything that has moved. Most of the objects it finds are known, previously discovered asteroids, but every now and then it will flag a new one. This new object's position is then reported to the Minor Planet Center, a global clearinghouse for this kind of data. Other observatories around the world will then perform follow-up observations to confirm the discovery and to precisely calculate the new object's orbit. This quiet, patient, and globally coordinated effort has been incredibly successful. We have now discovered over 90% of the very large, dinosaur killer-sized asteroids, those larger than 1 kilometer in diameter. And the good news is, none of them are on a collision course with Earth for the foreseeable future. The quiet work of these surveys has essentially eliminated the threat of a surprise, civilization-ending impact. But what about the smaller objects? The ones the size of the Tunguska or Chelyabinsk impactors? These are much more numerous and much, much harder to find. They are so small and so faint that our current ground-based telescopes can usually only spot them when they are already very close to the Earth, sometimes only a few days before they make a close pass. This is the quiet, ongoing challenge of planetary defense. To help manage and communicate the potential risk from these objects, scientists have developed a special scale. It's called the Torino scale.
It's a simple, color-coded scale from 0 to 10 that is used to categorize the potential threat of a newly discovered asteroid. A 0 on the scale means there is essentially no chance of a collision. A 1, which is colored green, means there is a very small but non-zero chance of a collision and it merits careful monitoring. A 10, which is colored red, would mean that a certain global catastrophe-level collision is going to happen. The quiet and very reassuring truth is that in all the years we have been tracking asteroids, no object has ever been rated higher than a 4 on the Torino scale. And that was only for a very brief period before further observations showed that it was not a threat. Almost every new asteroid that is discovered is immediately rated at a 0. The Torino scale is a quiet, calm, and rational tool that allows scientists to communicate the risk to the public without unnecessary hype or alarmism. It's a way of turning a scary idea into a manageable scientific problem. And to improve our ability to find these smaller, more numerous asteroids, we are building new and even more powerful survey telescopes. The most exciting of these is a future space-based observatory, currently named the NEO Surveyor. This will be a dedicated infrared space telescope whose only job will be to hunt for asteroids. By being in space and by looking in infrared light where these dark objects glow with their own heat, it will be able to find a huge number of the smaller, Tunguska-sized asteroids that are currently very difficult to see from the ground. It will be our quiet, watchful sentinel in the sky.
So, we are getting very good at finding these objects. But what can we actually do if we find one that is on a collision course with Earth? For a long time, the answers were purely in the realm of science fiction, often involving a brave team of oil drillers and a nuclear bomb. But in recent years, we have taken the very first, quiet, real-world step in learning how to defend our own planet. This is the story of the DART mission. DART stands for the Double Asteroid Redirection Test, and its mission was a beautifully simple and elegant one. The goal was to test a technique called the kinetic impactor. The idea is simple. You crash a heavy, fast-moving spacecraft directly into an asteroid to try and nudge it just a little bit, changing its orbit. If you can do this far enough in advance, even a tiny, tiny nudge can be enough to make the asteroid miss the Earth entirely years later. The target for this test was a binary asteroid system called Didymos. This system consists of a large asteroid, Didymos, which is about 780 meters across, and a tiny little moonlet asteroid named Dimorphos, which is only about 160 meters across and orbits a larger one. The DART spacecraft was not aimed at the big asteroid, it was aimed at the tiny moonlet Dimorphos. The mission launched in November of 2021 and spent the next 10 months on a quiet, lonely journey through the inner solar system, slowly making its way to its target. The spacecraft itself was not very large, about the size of a small car. It had no explosives, its only weapon was its own mass and its own speed. The final hours of the mission, in September of 2022, were a stunning and deeply moving demonstration of our technological prowess. For the last 4 hours of its life, the DART spacecraft was on a completely autonomous kamikaze run. Its onboard navigation system had to distinguish its tiny target, the moonlet Dimorphos, from the larger asteroid Didymos, and then guide itself to a perfect head-on collision. The spacecraft was sending back images to Earth in real time. And the final few minutes of that image stream were absolutely breathtaking. The world watched live as this tiny, fuzzy blob of a moonlet slowly grew larger and larger on the screen. It resolved from a blob into a distinct, egg-shaped rubble pile asteroid. In the final seconds, you could see the individual boulders and rocks on its surface in incredible detail. The final image, sent just before impact, was a close-up of a small patch of the asteroid's rocky surface. And then, the signal went dead. The spacecraft had hit its target, 11 million kilometers from Earth, with pinpoint accuracy. It was a perfect bullseye.
The impact itself was observed by telescopes all over the world, and even by a small Italian-built CubeSat that DART had released a few days earlier to fly by and photograph the collision. The images showed a spectacular, brilliant plume of dust and rock being blasted out from the surface of Dimorphos. But the real question was, did it work? Did the impact actually change the little moonlet's orbit? After several weeks of careful observation, the answer came back, and it was a resounding yes. Before the impact, Dimorphos orbited its parent asteroid every 11 hours and 55 minutes. After the impact, its orbit was 32 minutes shorter. The tiny spacecraft had successfully and significantly altered the path of a celestial object. It was the first time in history that humanity had deliberately moved a planet, or at least a tiny moonlet. It was a quiet, beautiful, and deeply hopeful proof of concept.
The success of the DART mission was a monumental achievement. It proved that the simple, elegant idea of a kinetic impactor is a viable strategy for planetary defense. It was a quiet, historic moment, a transition for our species from being passive observers of the cosmos to being active participants, capable of shaping our own destiny. Now, it's important to remember the scale. The DART mission was a test. The asteroid Dimorphos was never, ever a threat to Earth, and it was a very small object. Deflecting a much larger, dinosaur killer-sized asteroid would be a much, much greater challenge, likely requiring a much larger impactor, or perhaps even multiple impacts, or other, more advanced technologies. But DART was the crucial first step. It has given us a wealth of real-world data that will allow us to refine our models and to plan for future missions. The upcoming European Space Agency mission, Hera, will travel to the Didymos system in a few years to study the aftermath of the DART impact in detail. It will measure the exact mass and composition of Dimorphos, and it will study the crater that DART created. This will give us an even better understanding of how asteroids react to being hit by a spacecraft. This quiet, growing, and international effort to find, to track, and now to learn how to deflect these cosmic visitors is one of the most hopeful and important stories in all of modern science. It is a story of our species, slowly, patiently, and cleverly learning how to protect itself. It's a quiet and profound maturation, an acknowledgement that with our growing technological power comes a deep responsibility to be good guardians of our own small, beautiful, and fragile world. And so, our long and quiet journey through the history of our planet's cosmic collisions comes to its close. We have traveled back billions of years to witness the colossal, world-shaping impacts that created the Vredefort and Sudbury structures. We have stood at the edge of the Cretaceous period and watched the fall of the dinosaur killer. And we have returned to our own time to see the flash of the Tunguska and Chelyabinsk events and to witness our own first tentative steps in learning how to defend our home. The story of asteroid impacts is, on the surface, a story of violence and destruction. But I hope that tonight you have found a different, quieter perspective. It is also a story of profound and constant change. These events, as destructive as they are a fundamental part of the cosmic cycle. They are not a malevolent force. They are just a quiet, random, and deeply impersonal part of living in a dynamic and ever-changing solar system. And they are a story of creation. The impacts delivered the water and the organic molecules that may have been the seeds of life itself. And the great Chicxulub Impact, for all the life it ended, also cleared the way for the rise of our own mammalian ancestors. Our own existence is a quiet, accidental consequence of one of these great cosmic scars. And finally, it is a story of hope. For the first time in the 4.5 billion-year history of our planet, a species has evolved that is capable of understanding this threat and of doing something about it. Our quiet, patient vigil of the skies, our ability to find and track these ancient travelers, and our first successful attempt to change the path of an asteroid is a profound statement.
It is a story of our own growing wisdom and our ability to take responsibility for our own survival. And in that, there is a deep, quiet, and profoundly comforting peace.